Hello everyone, this is Arnab Kaviraj, a PhD student in the Department of Electronic Systems Engineering, Indian Institute of Science, Bangalore. Today I'll be discussing a little about our recent work on high throughput discovery of high Curie point 2D ferromagnetic materials. This has been published in the journal NPJ Computational Materials, and this is the DOI cum URL of the paper. You can find the paper here. So there is a little bit of story to tell here. Magnetism in bulk materials has been studied for many years, and the phenomena of magnetism is pretty well understood in bulk materials at this moment. But magnetism in 2D materials is pretty new. One of the reasons is so theoretical physicists actually used to doubt whether the existence of 2D magnetism is really possible at finite temperatures. For example, in this classical paper by Marmin and Wagner, they have shown using an rigorous isotropic Heisenberg model that magnetism in 2D or 1D cannot exist at finite temperatures. Finite means it is non-zero and positive. However, very recently, in at the end of 2017 and 18 and even 19, we have seen that people have been discovering magnetism at in 2D materials. So this paper is for the material CRI3. This paper is for the material CR2Ge2 T6. So both of these materials show magnetism at finite low temperatures, around maybe 70, maybe 43 and below 43 degree or below 70 degree. These kind of Curie temperatures. And very recently, people have actually shown that in VSE2 monolayers, there could be even room temperature magnetism. So, what brought upon this apparent anomaly? Actually, the Marmin-Wagner restriction has been basically these materials, these specific 2D materials where magnetism has been found so far experimentally, these actually show pretty great magnetic anisotropy, which means the magnetic moment prefers to be oriented in one direction only. And this actually lifts the Marmin-Wagner restriction. That's why people have been observing experimental two-dimensional magnetism these days. And so after these discoveries, a huge interest has been drawn to 2D magnetism, and people have been trying to discover new 2D materials, new 2D magnetic materials continuously. Okay, so this is a one slide primer on Curie temperature and naturally occurring magnetic states. This has been actually taken from Wikipedia, so anybody can go and check it out in details. So you can see, so first of all, we have to understand where this magnetism come from. So basically of electron spins, the atoms of a magnetic material acts as little magnets. So there could be billions of tiny magnets in a magnetic material. But how they are arranging themselves, that actually decides what kind of magnetism we are seeing from the material, or whether we can see magnetism from the material at all. So ferromagnetism is when these all atomic magnets, all these tiny magnets line up nicely towards one direction only, and then only you can get a net magnetic moment from the material. So this is called ferromagnetism. However, with increasing temperature, so this can be observed at low temperatures usually. As you go on bringing the temperature up, the temperature will distort this small magnets. So their order will be distorted a little with the thermal energy. So they will tend to point in random directions as you increase the temperature. So without magnetic field, without any magnetic field, after a certain temperature, these will actually be oriented in really completely random directions, where there will be no net magnetic moment from the material. So suddenly macroscopically you can see that the magnetism of the material suddenly goes down above some temperature. That is called the Curie temperature. However, if you apply a magnetic field even beyond Curie temperature, the magnetic field actually lines up the atomic magnets. So this is a natural paramagnetic state. This state is called paramagnetism. This is paramagnetic state, and so without any applied magnetic field, a ferromagnetic material looks like this below Curie temperature, and above Curie temperature it looks like this microscopically. Excuse me. And so you cannot see any amount of magnetism beyond Curie temperature even from a ferromagnetic material. So there are other kind of magnetism where there could be ferromagnetism, where there could be tiny magnetic moments could be lining up in different directions, but there should be an order, a symmetry constrained order. But you can see the arrow sizes are different here. That means that magnetic moment in the up direction and in the down direction are different, and so the down direction magnetic moments cannot cancel the up directed magnetic moments completely, and even there are equal number of up and down arrows, you will still see some kind of total magnetic moment in this direction. However, in case of antiferromagnetism, there are equal amount of up and down oriented tiny magnetic moments, atoms, whatever you say, and they cancel out completely. So in antiferromagnetism, even below Curie temperature, you won't be able to see any macroscopic magnetic moment, total magnetic moment, but there is a magnetic order which is called antiferromagnetic order. So we are mostly concerned about ferromagnetism and paramagnetism in this study, and this temperature, this Curie temperature, this is very important for new magnetic materials. We need to know that Curie temperature of them, and we need to know whether, so we know our real life device operating temperatures, right? Most of these are beyond room temperature. Most of these are even high temperature, maybe 100 degrees centigrade. Maybe some device acts at 100 degrees centigrade. So the Curie temperature is actually a very important parameter to know for magnetic materials. So I won't go into details about 2D materials in this presentation. However, the recent trend in 2D materials is people have been using computational top-down and bottom-up approaches. Top-down approaches like computational exfoliation, bottom-up approaches like maybe random search, maybe substitution. People have been predicting a lot of 2D materials, with varying properties, varying different kind of desirable properties, and these materials. So the two large 2D material databases I have listed here. So one is C2DB, the second is 2D Matpedia. So these are the relevant papers. And these databases are open databases, by the way. Anybody can visit these databases. So these databases actually they actually contain thousands of two-dimensional materials. However, a lot of materials among these are magnetic materials. These material databases are general purpose material databases, and they do not contain the Curie temperature, because that falls under scope of a different study, which is the main objective of this study. To determine the Curie temperature, you have to go through a lot of trouble computationally. So in this paper, what we have done, we have gone through these databases, and we have predicted the Curie temperature of these 2D magnets using powerful computational tools. These you have to go to a lot of trouble to determine the Curie temperature computationally or even experimentally for a lot of materials. And in the following slides, I'll explain why this is difficult. I'll explain the process in detail. So this is the crystal structure of CRI3, the first Two-dimensional material to be experimentally exhibit two-dimensional magnetism. So these blue balls are actually the chromium ions, and these are brown, right? These brown balls actually represent the iodine atoms. And these arrows, from these arrows you can see these arrows actually represent the up spins and down spins states of the chromium ions. So chromium being a magnetic ion, it acts like a tiny magnet. It acts like tiny magnets, and depending on their order, you will depending on their order you will get to know what kind of magnetic state they usually line up in. So these four configurations. So here FM means ferromagnetic and AFM means antiferromagnetic. These four configurations has been generated by a code, an automated process. So if you provide the crystal structure, which is this, the position of the atoms in a cell with a specific lattice parameters. If you provide the crystal structure information to a automated module called PyMatGen, it actually gives you back these configurations. These are symmetry allowed natural spin state configurations. So actually these has to be known, these has to be examined to determine the Curie temperature. This is probably the first step of determining the Curie temperature computationally. So these all of these structures, when you calculate the energy, so we calculate the energy here using density functional theory. It's a pretty well known tool in the material science community. So using collinear, so this is called collinear spin states, where the spin can be only the spin can point in only two directions, either up or down. So from these collinear spin calculations, we try to find the ground state, which is the energetically most favorable state, the state which has the lowest energy of them all. So after examining this PyMatGen generated spin configurations, mind that these are always symmetry allowed. So asymmetric configurations are usually not allowed in nature. Okay, so after determining the collinear spin collinear out after using after using collinear density functional theory, DFT, we determine the energy of these spin configurations. We'll call these spin configurations, and we see indeed the ferromagnetic state is the ground state. This ferromagnetic state is the ground state, but and these antiferromagnetic states, these have higher energy. So naturally, this is the ground state, and this is the most stable state. Um, Having explained about spin configurations in the previous slide, now I am equipped, we are equipped rather, to understand our workflow for determining the Curie temperature from the crystal structure. So you can think of this as a box where you can insert the crystal structure and it spits out the Curie temperature. But what goes into this box? So we'll zoom in now here. So the first step, the first block here is PyMatGen, a recently developed module of PyMatGen. PyMatGen is a very useful Python library, a set of very important Python tools for material scientists. So a recently developed module of PyMatGen actually can take this crystal structure and then can generate symmetry allowed different spin configurations. So you can think of these as the different spin configurations. Maybe this one is FM and these ones are AFM spin configurations. Then using collinear density functional theory, we calculate the energies of these spin configurations. So this E is the energies rather, of the spin configurations. We also can get the magnetic moment of different atoms in the system. So what amount of magnetism they show, that is in simpler word, it's called magnetic moments. It could indeed turn out that the material is antiferromagnetic, that means the ground state of the material, the most energetically favorable state of the material is antiferromagnetic. We discard the material then because a lot of material do turn out to be antiferromagnetic. Antiferromagnetism is probably more common than ferromagnetism in nature, and we're interested in ferromagnetic materials only. If it does turn out the ground state is ferromagnetic, the material is ferromagnetic, we go to a separate step where we use non-collinear energy calculation, again using density functional theory. So non-collinear energy calculation means that the spins don't get to be either in up or down directions, but you can orient the spins in arbitrary direction in a 3D sphere if you like. And what we do, we indeed orient the spins in different directions and we calculate the energies from them. From this, what we get is the easy magnetization axis, which is the direction where the energy is lowest when you orient the spins in that specific direction, that specific crystallographic direction. And we also get the amount of anisotropy, which is the amount of difference in energy, the amount of gain in energy or loss in energy when you change the direction of the spins. So this actually helps us, all of this data actually helps us to do a model fitting. So what we use here is called an anisotropic Heisenberg model. You remember probably under Marvin-Wagner restriction. Under Marvin-Wagner restriction, 2D magnetism cannot exist in 2D using isotropic Heisenberg model. But we use the anisotropic Heisenberg Hamiltonian here, which actually takes into account the anisotropy as well as the exchange. So we fit the so from these energy calculations we have enough data to fit the model Hamiltonian, and from this model Hamiltonian we actually get two kind of parameters. One is J and one is K. J being the exchange parameters which are obtained from this collinear energy calculations, and K is the KR, the R rather, K are the anisotropy constants which is obtained from this non-collinear energy calculations. And then we we magnify the crystal in a large, we make it infinitely large, not infinitely actually per se, but very large, and using something called a just-in-time compiler, which actually makes the Python codes pretty fast. You can check out the paper about the details. We do a neighbor mapping, which is actually a computational step to make the things easier, and then we perform what is called a Metropolis Monte Carlo simulation, which is again powered by JIT compiler, because Python being an interpreted language, the Monte Carlo would be pretty slow if we didn't use this compiler. And using this JIT compiler, we use the Metropolis Monte Carlo using these parameters J, K, mu, and these parameters. And from this Metropolis Monte Carlo algorithm, we actually get from this we actually get to decide the Curie temperature of the material. So one more thing to say here. Here we have actually indicated the approximation usage of CPU and GPU. So this has been done in a hybrid machine where we have CPUs as well as GPUs. So GPU accelerated machine, and the amount of CPU and tentative CPU and GPU usage, approximate CPU and GPU usage has been given here in bars. So you can see this Monte Carlo is almost fully based on CPUs, whether this neighbor mapping is almost fully based on GPUs. One more thing to mention here, that there could be, if you imagine this to be a box, this box actually can be replaced with machine learning. So this will be a regressional learning. So this will be a regressional learning, but this box can actually be replaced using machine learning if you have a powerful featureizer and also a lot of data. This box where this decision is being taken whether the material is FM or AFM, this can also be replaced provided that you have enough data to fit the machine learning model. So using the methodology I have shown in the previous slide, we develop a high-throughput code, a Python code, which is capable of running this set of calculations in a high-throughput manner. And we start with C2DB, which was very convenient because the authors have made a primary distinction between FM and AFM materials. So there are almost 800 materials classified as ferromagnetic in C2DB. We start with this 800 ferromagnetic 800 materials classified as FM, and we encounter these crystal structures. So these different prototype structures, these different crystal structures we have encountered while scanning the scanning the complete C2DB database for ferromagnetic materials, while scanning the 800 material classified as ferromagnetic. So the blue balls here represent the magnetic ions, and the other colors represent the non-magnetic ions. So you can see the variation of structures here we have encountered during our search. A lot of these materials, around 50% actually, turned out to be antiferromagnetic upon close inspection by our code. A lot of material could not be, a lot of calculation for a lot of material could not be finished because of several computational challenges, which we have detailed in the paper. In the end, we could successfully determine the Curie temperature of 157 materials. 157 materials were verified to be ferromagnetic, and we could successfully determine the Curie temperature of these 157 materials from C2DB. And we use these 157 data points as a training set to a machine learning model. And we also build a test set. I'll explain in the next slide how we have built the test set for the machine learning model, which we train using the data obtained from C2DB, the 157 data points obtained from C2DB. I've mentioned something called exchange constants, which were represented using J in the previous slide. So I'll try to explain what is exchange here. So exchange is, in very simpler words, in a very watered down version, exchange energy. So this is an energy term, energy per atom, probably energy per link. So exchange energy is when you substitute one upspin electron, when you exchange one upspin electron with a neighboring downspin electron, and the amount of change there is basically called the exchange energy. That is it is actually in units of energy per link. So there are two kinds of exchanges, where one is called direct exchange, where the magnetic ions, the exchange coupling between magnetic ions are not influenced by any anions in between. So there are no anions in between here. You can see these two magnetic ions should actually show something called a direct exchange, because this exchange is not happening through any anions. No anions are there to influence this exchange. Another kind of exchange is called super exchange. So probably these two atoms are connected, are coupled through super exchange, because this is an anion, this is a non-magnetic ion, this is an anion, and this exchange is mediated by this anion. So this is called super exchange. There could be other different kind of exchanges, which I won't go into details here. So this slide is basically about tiny detail, about telling you a tiny detail, tiny but significant detail of calculating the exchange energies. So I have explained what is direct exchange, what is super exchange. Um, so what have been done in the literature, for most of the literature actually, not all of them obviously. So people have been actually taking the nearest neighbor model. Well, they assume that the nearest neighbor is only influencing the exchange, and the other neighbors, the next nearest neighbor, probably second next nearest neighbor, these won't influence the exchange at all. But for these specific crystal types, so here we are talking about the crystal types where there are several layers of crystal ions. So you can see one layer here, sorry, magnetic ions. So different layer of magnetic ions. So you can see one layer here, one layer here. You can see one layer here, one layer here, third layer here, one here, one here. These are all side views, by the way. So one layer here, one layer here, one layer here, one layer here. So this multi-layered for these multi-layered magnetic ion structures, you have to actually take the next nearest neighbor model and probably the influence of the other nearest neighbors as well. So in this work, given enough data, enough configurations, we have taken up to the fourth nearest neighbor. And you can see here the distance between these neighbors. So this is 2.82. This is for a specific material CR2C. This distance between the nearest neighbor and next nearest neighbor is very small, 2.82 and 3.19. So you can see that the next nearest neighbor and probably the second next nearest neighbor or third next, even the fourth next nearest neighbor interactions are also necessary to predict the Curie temperature properly. Here is another kind of crystal structure where the inclusion of higher neighbors is necessary to calculate the TC properly. So again, you can see these are square. These are all top views, by the way. So these are usually square or rectangular lattices where the nearest neighbor could be here and the next nearest neighbor could be on the corner of the square or rectangle, or even vice versa. And you can see the difference in distance between nearest neighbor and next nearest neighbors are not very large. So also at the corners maybe there is direct exchange at play, but between these maybe super exchange is at play. So this kind of exchanges has to be taken into account, right? So maybe here is direct exchange and maybe here super exchange. So these kind of different exchanges has to be taken into account to calculate the TC properly. So this is another kind of crystal structure, square or rectangular crystal structure, than the structure I have shown you in the previous slide, where there are multiple layers of magnetic atoms. These two structures actually, for the calculating TC properly for these two structures, these two kind of structures, you need to take into account take into account the effect of the higher neighbors, possibly up to the fourth nearest neighbor as well. So here I can show you the prototypes of unique test data. So like I told you, from C2DB, the 157 data points we have got from C2DB, we have trained a machine learning model training on those 157 points, and to test the accuracy we apply this on a separate test data set. This test data set actually includes a lot of selected materials from the literature. So these materials, so this CR3T4, this is a pretty famous material from the literature, promising to show high TC. So these row are all side views, by the way, but these are all top views, right? So these are all top views, these first two rows, and this third row is a side view, are the side views. Yes, so these a lot of these materials are taken from the literature, and a lot of these materials are taken from 2D Matpedia, the second database I've shown you earlier, right? So again, you can see these actually have very complex geometry as well as very complex composition. So you can see ZnNi2O5, Mn2P4O13. So these are large structures with complex composition as well as very complex structures. When I say that we have used machine learning model to train the data, what I actually meant, which I'll go into details here, what I actually meant that we have performed an AutoML search on the dataset. So it's actually much different from training. This AutoML search has been done using this tool, uh, developed by a group in the Lawrence Berkeley National Laboratory. This is called AutoMatMiner, a very useful tool indeed, and freely available, by the way, open source. And this picture is taken from their website only. So this is their website. So here you can see something similar to what I have shown you earlier. It's like, again, it's like a box. Here a crystal structure, this is a crystal structure goes in. and the prediction comes out, right? So here they have used something called KVRH, but we would like to predict TC. So for that we have our own data set. So what goes into this AutoML pipeline? So this is called a pipeline. There are different parts of it. I'll try to explain now what different parts of it does. Different part of it too. Parts. Okay. So the first step is featureization. So there is, again is something called auto featureization. This auto featureization is done using another tool, another set of computational tool developed by the same group, which is called mat miner. So if you remove this auto part, there is mat miner. So using mat miner, this auto featureization is being done based on only two properties. One is composition and one is structure. So you can see a very valid and pretty easily computable physical as well as chemically meaningful features. So the dataset is decorated with this kind of features. Then another module of Automat Miner does a cleaning. So basically missing data handling, encoding and these kind of things. Then reduction happens. So feature reduction, this kind of feature reduction algorithms are used, and then it goes through AutoML. So again for this AutoML, a library named Teapot has been used. And you can see here a kind of a schematic. So this is the model space. So you have probably heard of these different models. There is SVM, support vector machine, the famous support vector machine. There is deep neural networks. There is random forest. There is gradient boosting. There is lasso regression, and you can see they make up the whole model space. And you can see there are maximas, there are minimas. So ideally, we would like to find these minimas, and we'd like to find the best model from this model space for a given dataset which you have entered into this pipeline, right? So that is basically AutoML. And by the way, hyperparameters are also tuned, which here they haven't shown, but hyperparameters are also tuned at the same time, and this kind of training goes on. So it's much more expensive than a normal machine learning model training. It's much more expensive. It goes on for days probably, even for a small data set like 157 data points. So using these kind of tools, we have developed, we have found the optimum machine learning pipeline, and we have trained this using that we have fitted this using that 157 data points obtained from C2DB using a combination of density functional theory and Monte Carlo. Right, I'll show you the results in the next slide. So here are the results of our machine learning pipeline, which we have obtained using AutoML search of the model space as well as the hyperparameter space. So these blue points are the training data points. So you can see for training data, the model has fitted them beautifully, almost perfectly for most of the points, maybe a few outliers here and there. But for test data, the fitting is not very good. Actually, you can see few points are pretty accurate. The prediction for few points are pretty accurate, but for a lot of points, it's not accurate. So the reason for this, the probable reason for this, we have speculated in our paper. Please go check it out. And here is the absolute error distribution on a combination of train and test data. So you can see the most of the errors are pretty small and almost negligible. We are almost at the end now. So in this slide, I'll try to conclude the results from this study. So so we actually like to classify the results obtained from this study as a threefold result. So the first part is the computer code, which actually eliminates present practice of heuristics based TC calculation. So using automation, we have actually generated the spin configuration. So this is not a heuristic based process, but for most of the literature, people have done it using heuristics, manual process. So there is always chances of missing some spin configurations. But because we use a structured library, a structured search, so the chances of missing out on specific configurations actually are very small, and the process becomes fully automated. Using this computer code, we actually can scan 800 to almost 800 2D materials, and this actually does the first principle based calculations, the Heisenberg model based Monte Carlo simulation, and this can be done using a high throughput fashion in even a GPU accelerated workstation. The second part of the results is the database, is a sub database rather, of 2D ferromagnetic materials with TC. So by examining all of these materials, we actually found a total of 29 2DFM materials with TC greater than 400K, that is 100 degrees centigrade, and 35 materials with TC greater than equal to 300K, that is the room temperature, right? So these materials can actually shows promise to be used in real life devices where the temperature can go pretty high, but still this material would retain their ferromagnetic property, and so you can use them in the various devices. So uh, and the TC predicted for by our automated code for experimentally synthesized materials like I've shown you, CRI3, CR2, GE2, T6, VESC2, MNSC2. This is actually pretty close. So our predicted value using our high throughput code is pretty close to the experimental observations, so which actually validates our high throughput methodology as well. And we discovered many important magnetic materials like metals with low magnetism like MOW and TI, which have so far been ignored by this kind of heuristic based formula screening. The third part of our results is the ML model to complement the computer code, right? So using 157 data points, we have developed this machine learning based model. This we have done using a extensive search of the model space as well as the hyper parameter space. So the machine learning pipeline rather is pretty robust for this kind of usage. And with more data, this model can be refitted. This model can be refitted, and the accuracy can be increased, right? uh, and this model ultimately with the availability of large amount of data, ultimately this model could actually outperform our DFTMC based rigorous code. So if trained with a sufficiently large data set of 2DFM materials, this model actually might ultimately be able to replace the DFTMC based code, and ultimately this ML model can be used instead of the DFTMC based code for a rapid screening of magnetic materials. So these three are the main highlights of the results of this study. Again, I remind you to go please check out the paper. It is an open access paper. Anybody can go and read it in the website. And I thank you for your attention. Thank you.